Okay, for our next question, we want to figure out the Lewis structure for IBr2 minus. And so we need to remember to count that negative charge when we're counting the valence electron. So let's start with that. So for our valence electrons, we will have 7 coming from the one iodine plus 2 by 7 because it's a 2 bromine, and then we're going to add 1. So let's just label them. And this is because of the charge. And this is going to give us a total of 3 by 7, 21 plus 1, 22. So I have 22 electrons to distribute. So obviously we're going to put I in the middle, Br. Let's not start with the bonds, but I in the middle, we're going to have Br and Br. We do know that halogens like to make a single bond. So let's start with a single bond on each and try and fill out the rest of the valence electrons. Okay, and then let's see if it all makes sense. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so we see that we need 2 more electrons. And we cannot fit them on the bromine, but we will be able to fit them on the iodine in such a manner. And what you have here is actually called an expanded octet. Which only certain elements are permitted to have. So if we just quickly look at the periodic table, so elements beyond period 4, so including period 4 and beyond period 4, are going to be allowed to have something called an expanded octet, where it can accommodate for more than the 8 electrons. And the reasoning for this is because, so the reason why we say it can take 8 electrons at a time is because we usually have the s orbital taking 2, and we have the p orbital taking 6. But once we start having d orbitals, which occurs from period 4, including period 4, downwards, then you can make space for 10 more electrons. And so they say at the first year undergrad level that the d orbital is the reason why you have an expanded octet. It's more complex than that. But for now, just keep note that elements including period 4 and downwards can have an expanded octet. Above them cannot. So if this was something else like lithium for whatever reason, I wouldn't be able to account for those 22 electrons, but I wouldn't have 22 valence electrons to begin with. So this is going to be our final answer. Oh, and don't forget about you have a minus. Let's figure out which one that is on. So 2, 4, 6, 7. So 7 minus 7, 0. 2, 4, 6, 7. 7 minus 7, 0. 2, 4, 6, 7, 8. So here it will be 7 minus 8, which would give us minus 1. So the one negative charge is going to be on the I. And that's it. Okay, next up, we would like to get the formula for aluminum nitrite. So what we're going to do is use the crisscross rule, and that's when we're using when we have an ionic compound. You're going to use its oxidation / reduction state in order to get their formal charges. And so if we have element X, for example, and element Y with these respective charges, then we're just going to crisscross them. And when they combine, you get X, B, Y, and these are subscripts. Subscripts that you see in H2O. So for H2O, we have H that has a positive, plus O, which has 2 minus. So when you crisscross them, it becomes H2O. The two charges cancel because positive and negative, and that's it. And so for aluminum, we know that it is in group 3. So group 3 metal, which means that its charge will look like that. And for nitrite, we have a list here of common ions like hydroxide and sulfates and nitrate, including and phosphate, and they just have commonly known charges. So for NO3, it's going to be NO3 minus is what it's known as its charge. So when you just combine those two, we're just going to crisscross it like that. So Al will have a 1 here, and the 3 is going to apply to the entire thing. So not just the oxygen, so that it can become NO6. It's going to apply to the entire thing. So it's going to become NO3, 3. And so let's just write that up here. Sorry, it's NO2. Because we're doing nitrite, not nitrate. 52. And then if you just rewrite that in a cleaner form, because you don't need to write down the 1. And that is what the formula would look like. And just to give what this means, is that in order for things to be balanced chemically, same way that it was H2O, whenever we have H2O, it's oxygen and 2 hydrogen. The same thing is going to be applying here. We'll have aluminum connected to 3 nitrites, not with covalent bonds, but with ionic bonds, whenever you do have the molecules. And so that's what it would look like. Okay, on to the next question. We are looking for the Lewis structure of CH3+. So we can first calculate the valence electrons. And so we're going to have 1 by 4 because of carbon, plus 3 by 1 because of the hydrogens, and then we're going to subtract 1 because of this plus charge. That's going to give us 4 plus 3 minus 1. And that is going to give us 6. And I need to find a way to distribute those 6 electrons. So let's give us C, H, H, H. And let's start with some single bonds and fill in the octets, for example. So this would be 2, 4, 6, 8. That's too many. So what we're actually going to have here is an underfilled octet, and that is what is going to be responsible for that positive charge, because Carbon has 4 valence electrons. We have 1 from here, 1 from here, 1 from here, and it's missing that 1 more. So it's going to be 4 minus 3, leaving us with that plus 1. So this is what our final answer is going to look like for that one. On to our next question. We want the Lewis structure for CH2Br2. So again, we start with the valence electrons. So from carbon, we're going to have 4. And this is just by 1 because we have 1 carbon. From hydrogen, we're going to have 1, but that's going to be multiplied by 2 because there are 2 of them. And from bromine, we're going to have 7, but then there are 2 of them again. And so that's going to give us 4 plus 2 plus 14, and that's just a flat 20. Now let's figure out how to distribute them. You may be wondering why I chose this configuration specifically and not, like, for example, Br here. And that actually relates back to Vesper Theory, which I'll get into in a second. And so let's just connect them with single bonds. And so we see the carbon is happy, hydrogens are happy. Let's fill in our octets and see if all of those valence electrons have been accounted for. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So yes, they have been. And we don't have any formal charges because 2, 4, 6, 7. So the 2 bromines are going to be happy. Hydrogen has 1, when carbon has 4, 4. So there's not going to be any net charge. Now the reason why I put the bromines across from one another is to... So Vesper Theory is just a quick way to figure out what the geometry of the molecule would actually look like, and it's configured to minimize repulsion between electrons. Because we always favor the lowest energy configuration of a molecule. And so if we don't minimize that repulsion, then we're not minimizing the energy of the molecule. And so in this case, I want the bromines across from each other because these lone pairs, if they're next to each other, would repel each other a lot. So we want to keep them as far away from one another to minimize that repulsion. And so this would be the best answer if you just leave it like that. Okay, for our next question. So we want the Lewis structure for this. So again, we need to count valence electrons. And so this is in group 15. So you're going to have 5 multiplied by 1 from that, plus 3 multiplied by 7 from the fluorine, because each has 7 valence electrons and there are 3 of them. It's going to be 21 plus 5, which is 26. So we have 26 electrons to figure out where to place them. So of course, let's put the AS in the middle, surrounded by the 3 Fs, and let's start with some single bonds. And then let's fill in the octets for each of the fluorines because they're optimized for 1 bond and they have that already. Okay, and then let's see if we have any electrons left over. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 5. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we have 2 more left over, and that makes sense. AS does not have a filled octet, so the last 2 electrons just go right there. And we won't have any formal charges because 2, 4, 6, 7. So just in case you haven't been understanding how I've been counting those formal charges on each. There's going to be the number of valence electrons minus the number of lone pairs minus the number of bonding pairs, but over 2. Because remember, F is only contributing 1 electron here, and AS is contributing the other one. Maybe unequally or equally, that isn't our business right now. And so for F, we're going to have 7 minus 2, 4, 6. So 6 on the lone pairs, 7 minus 6. Minus has 1 bonding pair, so the bonding pair has 2 electrons in it over 2. And so 7 minus 6 minus 1, and that's 0. On AS, you're going to see something similar. All of the F's are the same, of course. 5 valence electrons minus the 2 lone pairs minus 2, 4, 6 over 2. And so that is 5 minus 2 minus 3, and that was also 0. So we have no formal charges, and that is our final answer. Okay, next up, we're going to find all of the possible Lewis structures for butane. So here we just need to note the fact that it's butene. That can easily be done by noting the structure of the formula, CnH2n with n is equal to 4, which is the but. Okay, and it's an E because of this fact. So we have butene here. And so butene, of course, has isomers depending on if you decide to make other singular chains, like you'll see. So first, let's draw the main structure. And we will have 1 double bond. So let's put it on the furthest side for now. And so this will be able to make 2 more bonds with hydrogen. 1, 2, 3, 1 more bond with hydrogen. This can make 2 more bonds, and this can make 3 more bonds. So what this is called is, if we count this way, and we're going to have to count this way because we want to encounter the double bond as soon as possible, this is going to be but1e if we label it. Next up, let's decide to move this double bond. And so let's have the double bond here instead. So this will be able to make 3 more connections. This will be able to make 1 more, 1 more, and 3 more. You can double check on each that you have 8. So 4, 4, same thing here, 4 by 4. And so now, if we, no matter which side you decide to come at it from, you're going to encounter the double bond on the second carbon. So here was on the first, that's why it was but1. Now it's on the second. So its label is going to be but2e. Okay, and now we can actually start creating links. Okay, so let's say we decided to, we can't move this carbon here because if you did, it would just be the exact same thing because I could just fold it back, if that makes sense. And so let's actually move this carbon link here. And so if we do that, we have that carbon linked here, a double bond C. And so this can make 2 more connections. This can make no more connections. This already has 4. This can make 3 more. And this can also make 3 more. Okay, and so this is going to be labeled differently. We're going to want to count from this side to encounter the double bond as soon as possible. If that double bond wasn't here, you'd be able to count from any side to encounter the methyl group on either side. And so this would be, has a methyl, 1, buttes on carbon 1. Oh, no, it's no longer buttes. Now the main chain is 3, so it's going to be prop. E. And that's what you have. So these are the 3 options. There's nowhere else where you could take this third one, because we put it on the other side. What we have is this one, just flipped over. And so we can only have these 3. Okay, next up, you want to find the electron configurations for each of the following. I'm just going to write them out over here. Okay, and then you can use the periodic table or Madeline's rule. Periodic table is the easiest one to use. If you want the shorthand, you're going to start with the shorthand. And so the closest noble gas to chlorine is neon. So we're just going to put neon in middle square brackets. And then we start counting. So this is going to be 3s2, 3p1, 2, 3, 4, 5. So 3p5. So 3s2, 3p5. If we'd like the entire thing written out, you can start from the top, which would be 1s2, 2s2, 2p6, and then that 3s2, 3p5. And so 1s2, 2s2, 2p6, 3s2, 3p5, land on chlorine. Okay, our next one, SP, let's find it first. It's right here. Okay, so the nearest noble gas, of course, is going to be krypton, right here. So you can't go to the one after it, you have to go to the one before it, and that's going to be krypton. We just put the krypton in square brackets, and then you begin counting again. So SB is here. It's in the 5th period. So we're going to have 5s2, 4d10, and then 5p3. So 5s2, 4d10, 5p3. If you want to write out the full thing from the top, then again, you just count. So 1s2, 2s2, 2p6, 3s2, 3p6. Sorry, skip the 4s. Here it seems. 4s2, 4p6, 5s. Sorry. I did include the 4s. Sorry, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, drop the number down by 1, so 3d10, 4p6, and then 5s2, 4d10, drop the number by 1, remember, and then 5p3 to get to SB. And then we have W, so let's find it. It's going to be right here. So we're going to have to pass some lanthanides, which include an F group, which is not too hard to deal with. And so if we want the shorthand notation, we need to find the closest noble gas. That's going to be xenon. So we have xenon. And then we have 6s2. And then we have the lanthanides, so drop it by 2. So 4F lanthanides can take 14. 5d10. Oh, we're not going all the way. So now that we're in the 5D group, we realize that it stops on the third one. So it's actually going to be 5d3. And that is going to be the final answer. D3, sorry. This is included. So 1, 2, 3, 4, 5d4. And then that's it. Yeah. And then if you want to write out the entire thing, as I said, just count from the beginning. So you're going to hit all the way until you get 5p6, and then you start the 6s2, 4f14, 5d4. Next up, PV. We want to find it first. And that's going to be right here. Closest noble is Xenon. Let's just put that in the square brackets. And then now we need to get to it. So again, we're going to be passing 6s2. 4f14 with the lanthanides. 5d10 because we get out of the transitions. And then we're going to have 2 here. That's going to be 6p2. And that's it for that one. And then lastly, we have CF. So again, we're going to need to find it. And it's actually inside of the lanthanides here. And so for the lanthanides are going to come before the D group when you're listing them down. So because we technically have not hit the D group yet, we're just going to have the S group. It is in this second row. So it's going to be in period 7. So we will have 7s, and then drop the number down by 2, so 5f, then you just count them. 2, 4, 6, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5f10. And so again, find the closest noble gas, that's going to be Rn. And then you're going to have 7s2, drop the number down by 2, 5d10. And that's going to be our final answer. And that's it for this question. 5f, sorry. The labels can get a bit confusing if you are rushing. So just be careful. But that, it's F. 10. Okay, next up we would like the Lewis structure C2H3N.